And welcome back, guys. It's time to do one more. We were discussing variable selection heuristics, and we looked last at heuristics that exploits the semantics of the problem. Now we're going to look at one that really looks back at the past, at the recent conflicts, in order to actually make better decisions going forward. And since it's first fail base, you know what the drill is going to be, right? If a conflict happened in the past, branch on that again. More conflicts is good. So let's take a look. Last conflict search is based on a simple idea. It's something that you use together with another heuristic, right? And let's call the other heuristic the fallback one. It could be MinDom, it could be WDOG, it could be impact-based search, activity-based search, it doesn't matter. We have another heuristic that we're going to use. That's the one that does the most of the work. But this one is overlaid on top. And the basic idea is that it's going to remember the last variable that caused the conflict to say, if we had a conflict and we backtrack, what we should branch on next is the thing that caused the conflict. Now, if we succeed and have no conflict, we forget we had one, and therefore, when we need to make a decision, we fall back on the fallback heuristic. That's the basic idea. It was described in this paper, and we're going to look in detail how that works and what's the intuition behind it, and then, of course, the evolution of that. Now, when we're branching on a variable that leads to a failure, we're following a path, right? So imagine here we're following a path, branching on x1, on x2, on x3, and then finally down here, we encounter a choice on variable x4, and it's not possible to fix it to some value. It turns out it's in conflict with something else, right? With x3, x2, x1, we're not sure what variable conflicts with it, but we basically are saying if it's in conflict with one of these guys, when we go back up, we should be branching on x4. Because as long as the conflict persists, we're not going to get out of this. We should first branch on the thing that triggers it. So that's the basic idea. So if we look at an example, start at the root node 1, we go down and we pick a variable y with the fallback heuristic and we branch on it, assigning it value c. We're now in node 2. In node 2, we make a branching decision and we branch on variable x, fixing it to value a, and we reach a node, the node number 3, which has a violation. So because it has a violation, we will remember that the last conflicting variable was x. When we go back up, we of course say we can't take value a, right? Because that's the only alternative. So we do that, but then we branch on x again, because that was the variable that last caused the conflict. So we will try node 5, trying value b for it, and then node 6, preventing value b, both conflicts, so we still have a last conflicting variable, which means that when we backtrack and we go back up, of course we disallow value c for y, but the next choice is going to branch on variable x again, because that was the last conflicting variable. Now, if we succeed, we forget we had the last conflicting variable, and from this point on, we'll just do the right thing through the rest of the tree. Now, we can generalize this idea to that of conflict ordering search, to not stop just at the last conflict, but really remember timestamps that are going to keep track of when a conflict was detected. So think of a timestamp as a logical clock that simply ticks up as we go through the tree, and we're going to remember when we see a conflict what the value of that clock was when the conflict was seen. And then when we decide to branch on a new variable, we're going to pick a variable that is the most recent in terms of the conflict it has experienced, and we'll branch on that first. So let's take a look at this, and of course this is where you can find details on the paper and the ideas. So here is a tree, right? And we have the root, we have two decisions. We take x equal a. When we go down that path, we pick y equal b, and we detect a conflict. At that point, the clock, the logical clock, is 1. So we remember in the table here that the timestamp for the conflict when we picked on y is 1. Note that for x, we don't have a conflict, so the value is still unknown, null. Then we backtrack. We go down and we say y cannot be value b. At that point, we need to branch because it has succeeded. So we're going to say, okay, let's pick a variable, for example, z, and try value c. We have a conflict, that's time step 2. So we would go right in the table, the timestamp 2. Then we backtrack, we go down, we branch, we find again a conflict, the timestamp for z gets updated to 3. The most recent time point where z was in conflict was clock 3, timestamp 3. Now when we backtrack, we go back up, we prohibit value a, and the question is, which variable should we branch on at this node? We consult the table and we pick the most recent conflict, which of course would be z that has a timestamp 3, so we would be branching on z, bypassing any decision on y in this case. That's the core idea in this specific one. Now, this is the algorithm. You can agonize over the detail of the algorithm. There is nothing too tricky, right? It's basically telling us that if we have a CSP and it's not completely empty, we'll say that, empty meaning the search tree is empty, we'll say that if there is no variable that caused a conflict, the number of conflict goes up to 1. We're then updating the clock, the timestamp, for that variable to the number of conflict we have. So this updates the clock and this updates the value for the variable, and then we return false. After that, we say that if every variable is fixed, so every domain size is 1, we have a solution we return. Otherwise, we go through the process of determining the failed variable, that is all those that have a timestamp that exists, that's positive, and that have more than one value. And if we have none, we fall back on the normal heuristic, so we still have our fallback. Otherwise, we're going to pick the one that has the most recent timestamp. So that's why we have an argmax. We pick the one that has the most recent timestamp among the failed one. Then we go ahead and we apply the heuristic for the value for that variable, and we recur on the costs on the two cases, whether we have assigned or we have branched on less than or equal to v or larger than v. That's how the original algorithm was described. The key is that this is a selection based on the most recent timestamp. This is the update of the timestamp inside the search. So again, that's something you can embed easily into MiniCP, and that should present no difficulty whatsoever. Now let's visualize a little bit how that works. Consider this simple CSP. So it's a trivial one, specially designed to show how things break. So first we have 4 variables that you see in blue here, x1, x2, x3, x4. They're all binary and they have no constraints on them. And then we have 4 red variables, 5, 6, 7, 8, and they must all be different. So it's an all different on these guys, right? So every single one has a degree 3 because it can't be equal to the other guys, and the domain are 0, 1, 2. Now 4 variables, 3 values, and everybody has to be distinct. You already know that this constraints will doom that CSP. It's infeasible because of this part. All right, how easy is that going to detect, right? How easy are we going to do that? So if you go with a lexicographic ordering and you pick the variable with the smallest domain, well, all the 4 blue variables only have 2 values in the domain, so you will be tempted to branch on these guys first with min_dom. These guys have 3 values. You're not going to look at them right away. Notice that at the root, if you're not using the global or different, if you're using the pairwise distinct, you can't filter any values from this. So all the variables, all 4, have exactly 4 values in their domains. 3 values, sorry. So at this point, we branch and we branch on these guys. So what's happening? Well, this is what's happening. We branch x1, x2, x3, x4, and then finally we enter and start branching on the guys in the red part. We branch on x5, and the moment we've done that, when we hit x6, we'll discover the conflict. So we're going to discover the conflict, and we're going to repeat that for every choice of x1, x2, x3, x4. And that is the unfortunate part, because we're going to repeat that red tree for all the combination. This is a huge amount of work that we'd rather not do. Note that if we were to correctly branch first on x5 and x6, we would discover the conflict and never look at the 4 others. As a result, the entire tree would be substantially smaller, which is the big gain, right? This is the ideal tree if we were to recognize that we have to branch on x5, x6. Now I hear you, this is a little bit overdone, because if we were using the all different constraint, the global constraint, we would at the root discover the infeasibility. That's true, but let's keep on assuming that we're working with the decomposition. Now, what we want with COS, most recent conflict, is to sort of figure out in the search that this is what we want, even if we start from this far less favorable tree. Is that going to happen? And the answer is, of course, yes. Let's take a look. We branch on x1, then on x2, then on x3, then on x4 as before. Then we branch on x5. Then when we try x6, we discover the conflict. So because we know it's in conflict, we backtrack. We, of course, try the other alternative for x4. And here we branch on x6 because that was the most recent one that had a conflict. So x6 will be first. Then x5 will discover the problem. And again, now x5 will have a most recent timestamp, right? So when we backtrack and go back up, we try the alternative for x3. Now because x5 was the most recent, we branch on it first. The conflict is discovered on 6. And we say, damn, 6 is the most recent one that has caused the conflict. Let's backtrack. We go back up. We branch on the alternative for x2. Because x6 was most recent, that's the first we branch on. Then on x5, we discover the conflict. x5 is most recent, we backtrack. We take the other path for x1, and guess what we do now? We branch on x5. And because we branch on x5, we discover the conflict here. And the nice thing now is that we're just going to look at the alternative for that, and we're going to get something that looks a lot more like this tree, because there are only so many alternatives for the values we could assign to x5. We'll try 0, we'll try 1, we'll try 2, and then we'll discover we're done. So the rest of this tree looks like the ideal one. This part is what had to be done by the most recent conflict search to discover that we should first and foremost branch on x5 and then x6. That's the name of the story. That's what most recent conflict does. That's why it's useful. It's learning the right tree, even if your propagator wasn't strong enough to discover it on its own. With that, it's a wrap on the variable selection heuristic, and what we'll do next time, of course, we'll dive in the dark, dark world of value selection. See you next time.